The foundations of quantum physics took decades to uncover, and it was the work of many people: Einstein, Bohr, Heisenberg, Schrödinger, and others. Part of the reason why it took so long was that basic ideas about the nature of reality had to be abandoned. The idea of reality as a clockwork machine with definite causes leading to definite effects had to be surrendered. One of the first physicists to completely let go of the old ways of thinking was the young, brilliant Werner Heisenberg. In 1925, he published a series of bold new calculations outlining his approach to quantum physics. What Heisenberg did not know is that he had rediscovered an obscure branch of mathematics. This mathematics is called linear algebra, and it is not only the language of quantum physics, it is probably the most useful tool in all of mathematics. So how does this work? Imagine flying from London to San Francisco. Suppose there are 3 flights from London to New York, and 2 flights from New York to San Francisco. How many possible paths in total? Let's count them. 1, 2, 3, 4, 5, 6. This is a multiplication, right? 3 times 2 equals 6. Suppose there are 2 other direct flights from London to San Francisco. So we add these to our calculation. And now we get 8 paths in total. Hopefully this calculation is easy to understand. It may seem like this is too ridiculously simple to go anywhere, but what I'm doing with multiplying and adding paths really is how linear algebra works. And these path counting rules are precisely how to do calculations in quantum physics. I keep mentioning the word algebra, and I have a confession to make. Whenever someone starts showing me algebra, I look like this, and when I have to do algebra myself, well, I prefer to avoid this whenever possible. In quantum physics, these numbers we are calculating are called amplitudes. We are going to use this bracket notation for the number of paths from some origin to some destination. So the calculation goes from right to left, which is good if you are left-handed like me. From London to New York, there are 3 paths. From New York to San Francisco, there are 2 paths. And then we added 2 more direct paths. I'm going to mark this with a little d down here for direct. We found the total paths from London to San Francisco is 8. The whole calculation we just did looks like this using algebra language. 3 times 2 plus 2 to get the total paths from London to San Francisco. This gets much more complicated, but the basic idea is, instead of counting paths, you propagate a wave from the origin to the destination. So what can we do with this linear algebra? One idea is to apply this to randomness and calculate probabilities. Suppose we are going to roll the dice to decide where to fly to next. Starting from New York, there's 1 flight to Vancouver, and 2 flights to San Francisco, and 3 flights to Los Angeles. So what is the chance that we end up flying to Los Angeles? It's 3 in 6, which is the same as 1 chance in 2. This kind of calculation is so common that we sometimes write down half a bracket like this, and we call this a ket. For another example, think about a website. It has links to other websites. As people visit these sites, they travel on these links. Using the same mathematics of linear algebra, it's possible to rank the importance of websites just by counting paths from other important websites. This is the key to how Google works, and the algorithm is called PageRank. When Heisenberg wrote his paper in 1925, he just made up the mathematics that he needed. It was his mentor, Max Born, that realized this mathematics had already been discovered, but not many people knew about it. This is what became known as linear algebra. In quantum physics, we don't usually put big things inside a ket like this. It's just way too complicated. However, people are very seriously working on putting a computer inside a ket. This is extremely difficult, but if we succeed, we will have a quantum computer. We have been counting each path as one path, but quantum physics is even weirder than this. Sometimes a path is counted as -1. Then the paths interfere with each other and make the trip from London to New York impossible. Quantum amplitudes are not probabilities. Sometimes they are negative, and this just doesn't work as a probability. The rule for finding probabilities from quantum amplitudes is to rewind everything back to the start. This is a quantum measurement. In this example, we would get 8 times 8, which is 64.